Hi. Today we're going to take a look into some of the background behind how you can use EDTA to titrate. The reason we're doing some background is because unlike the other titrations we've seen, we're not really titrating an acid or a base, we're titrating a metal. And so that bears a little bit of talking about how that works. What's interesting is that this completely opens the door to several types of analysis, but I'll get into that as they come up. So interestingly, these things exist, and like an acid-base indicator, it's just simply any sort of chemical that would change color when it is bound to EDTA, and then have a different color when it's not. So our typical example here, I think we're gonna, well, not a typical example, but we have it here. When we have a solution, we're gonna have our beaker, and in the beaker, there's gonna be some magnesium ions, and there's gonna be some indicator ions. And obviously they are gonna have an affinity for each other. They need to bind to each other. Otherwise, this doesn't work. But then as you add EDTA, in the presence of EDTA, the EDTA kind of bumps out the indicator. And so then it would change color as the indicator is floating by itself, and then the EDTA is hanging out with the metal. So for that purpose, it's best to use these indicators that will bind to the metal, but obviously EDTA needs to be the preferential binder, because if the indicator has a higher affinity for the metal, you can add all the EDTA you want, the metal won't let go, the metal won't change color. That's actually going to open the door to some problems down the road. There are some alternatives to using metal ion indicators in your titration, which is like they are exactly the same as you would consider having alternatives in an acid-base titration. If you had an ion selective electrode, where the electrodes that we use for our digital pH probes are sensitive to H+, if they were sensitive to, say, magnesium, then you would be able to use those, and you can read the, instead of pH, you can read the PMG, and it would work exactly the same way. The only difference is, obviously, it wouldn't be centered on 7, but I'm getting ahead of myself in terms of the actual math. You could use a pH probe if you are using a slightly protonated form of EDTA. There's ways to get around that. Your book gets into it more. I'm not going to spend too much energy talking about it. So I wanted to take a look at some of the structures. We're going to look at this slide, this table for the next couple slides. This is the one I'm the most familiar with, Calmagite. You can see something pretty interesting. The free indicator color actually has its own colors to it. These metal ion indicators can also function as pH indicators, which opens the door to some wonderful, wonderful headaches. But you can see that some of them are quite useful in the colors that they indicate. So this one, right. So what I'm familiar with is the transition from blue to red. And you can see that that blue is kind of in between PK2 and PK3, and that is on purpose. We have a bottle of it in the lab. It's wine red right now because the Calmagite is bound to some metal. So you kind of have to think about how you would use that indicator in much the same way as how you would use that indicator in lab. If you were going to titrate an acid with base, you put phenolphthalein in the acid, it would be colorless. So just because you have a colorless solution, like, you can't just immediately assume that these things are always going to be existing free. There's a couple others. I'm much less familiar with them, but these colors are very numerous, but also quite important. They do function as pH indicators. So there are some potential problems, like here and here, I see a big issue. Even to a degree, I see an issue with these. And maybe both of these. I mean, look, my color blindness aside, if you have an indicator that in the absence of your metal is red, and in the presence of your metal is wine red, you're going to have a hard time hitting the target in your titration. Yeah, will you see the difference? Sure, but by the time you notice it, you may have overshot your equivalence point. Like I said, a good example here is this xylenol orange. Looking at this, 3 of the 6 protonated forms are yellow, the other 3 are violet. I would love to get myself a sample of this because I need to see how this works. In the presence of the metal ion, the complex is red. So a transition from yellow to red, I think you'd have a pretty easy time doing. That's exactly how methyl orange works. A transition from violet to red, well, it depends. It depends on the violet, depends on the red. It's going to be harder to see. So this already just opens the door to some potential problems you're going to have if you try and use these indicators just without thinking about it first. And that's the largest thing I can tell you about metal ion titrations. There's a lot more thinking involved before the doing starts. There is a solution in using a spectrophotometer. Obviously, if you have a hard time seeing between violet and red, a spectrophotometer has no trouble seeing between violet and red. But are you going to hook up a spectrophotometer where you're like adding your EDTA slowly or adding your metal ions slowly and you're like making measurements every drop? No, you're not. If you have one that's going to run continuously, that's great. But that's going to make things difficult. And the better solution here would be careful pH choice. So the Calmagite, like I said, I use the blue form. We usually buffer our pH around 10 or 11 to really hit in between PK2 and PK3 to hit that intermediate form there of the indicator. You could push the pH up above 12.5 and then you'd have orange to wine red, which would work just as well. The only hard part is getting a buffered pH above 12.4. You'd have to find some sort of buffered system that, of course, doesn't interfere with the metal ion, which is another one of the drawbacks to this whole process. There are a handful of ion indicator pairs that do. Like I said before, you need to make sure your indicator has a lower affinity for than EDTA does so that the EDTA can come in and grab the metal ion. Well, there are some indicators that do grab the metal too much. And that means adding EDTA is great, but you're not going to see anything. This ureachrome black T, it's apparently blocked by copper 2, nickel 2, cobalt 2, chromium 2, iron 3, chromium 3, not chromium 2, and aluminum. The best way to get around that, like say you were looking at copper, is you take your copper sample, before you add any indicator, you add a bunch of EDTA. And it's weird because you kind of have to almost act like your indicator is your reagent, your reagent. So you add a bunch of EDTA, and your copper will then, of course, bind to it. And then you would then add some of your indicator. So I'm gonna write EDTA here to indicate that we do have excess EDTA. Then you're gonna add indicator, which would then, you'd still have the same solution. Then you would slowly add in another metal, say like magnesium, which would eventually then trip, and now you'd have a mixture of this and that. Now the idea here is, yes, your indicator has a high affinity for copper, too high of an affinity, but of course when you're adding your indicator, you're adding minuscule amounts. So the idea here is that since you have excess EDTA, you add a drop or two of your indicator, yeah, the indicator might grab some of the copper, but there's so little copper once it's already at that equilibrium with EDTA, and that you can actually maybe get your magnesium to trip the indicator as well, and so you'll still get some data. And then the idea here is you would use your magnesium amount to figure out your excess EDTA, and then you'd have to go back to this original amount and subtract. We're going to take a look at an example of where that math, that stoichiometry starts to get involved. So kind of wrapping things up already in terms of just the background of titration. Direct titration is the one that we're going to go more in depth with in our next video, so I'm not going to take time to talk about it today. It works exactly the way you think it would, other than the fact that you're at a buffered pH. Take your metal sample, put in a drop of your indicator, add the EDTA until the EDTA has sopped up all the metal, and now the indicator changes color, and you're done. So, other examples of things that you can do. A back titration, which is exactly what I said in getting around the blocking problem of the indicator, is that you add excess EDTA, you titrate with a standardized second metal ion to figure out your excess. Of course, your second metal should have a lower binding constant than your first metal. If you use a second metal that has a higher binding constant, it's just going to kick out your first metal. Now, why would you do this? Why would you bother adding another layer? Well, taking a look at, well, obviously blocking, we just mentioned, but taking a look at your data, we have a bit of a problem if we want to exclude Calmagite with this red. That means that your pH really has to be like 8.1 or higher. Now, depending on the ion that you're analyzing, it's gonna precipitate. So the idea is you have your metal in an acidic solution, you add an excess of EDTA to grab up all the metal, you neutralize the solution, you dial the pH to exactly where you want it, the metal stays bound by the EDTA and does not precipitate. We saw that with the ammonia and the silver chloride way back earlier in the year. And the idea is then when you have this dialed solution, you have excess EDTA, and you kind of titrate the EDTA with a second metal, and then you do a bunch of math. So let me show you what that looks like. Here's an example. Nickel 2, right? So you can't have a nickel 2 solution. The xylenol orange indicator, 5.5 is where you want to target, but the problem is that pH is already too high, and you're going to get precipitation of nickel hydroxide, which you're not going to have an easy time analyzing with EDTA. You're not going to have an easy time analyzing with an indicator. So to make the solution easy to move around and analyze and actually like work up, you wash it first with EDTA. You take a 25 milliliter aliquot, wash it with 25 milliliters of EDTA. Yeah, see, this is the thing I don't like about back titration. You kind of have to have an idea of how much nickel you have already. Back titration, you're working blind, you're probably going to have to add a lot more than 25 milliliters. But then you neutralize, you dial the pH with a buffer, then you add more zinc. You add zinc now, and it says, yes, you've got your, well, I guess this question's kind of silly. It says it reaches the red endpoint. So the idea here is that when you have excess EDTA, your indicator is probably going to be unbound to a metal, and so the color we would see at a pH of 5.5 would be this yellow color here, and we're going to red. I think your switching point will be around 6.7, so that's why you're not going any further. I also understand that at a pH of 5.5, EDTA itself is not super active. We're getting there. It affects some of the math, but not all of the math. There's a lot to consider, like I said. Anyway, to try and figure out the molarity of the unknown, we just have to do a little bit of math. And the first thing I want to say is that we don't need, these are some low concentrations, we don't need to work in moles. But we do need to know amounts. So the idea is figure out amount of zinc added, figure out total EDTA, the amount of zinc is equal to the excess EDTA. So subtract. To get the nickel EDTA amount. So doing some math here, to figure out the total amount of EDTA, we're actually going to multiply 25 milliliters times our 0.05283 molar. It turns out when you multiply liters times molarity, you get moles. When you multiply milliliters times molarity, you get millimoles. Neat little trick you can do to save yourself one step. Now, I mean, that doesn't always work if your solution is significantly concentrated, because then you get obnoxiously large numbers. But in this case, you don't. You get, in this case, 1.3208 millimoles of EDTA. To figure out the amount of zinc, well, they tell us right there, 17.61 milliliters times 0.02299 molar, and that's going to give us 0.4049 millimoles of zinc. And so the idea is now we're going to say 1.3208 millimoles minus 0.4049 millimoles equals 0.9159 millimoles. And this is the amount of EDTA that actually participated in the original reaction with the nickel. So the idea is we added 1.32 total. By adding the zinc, we found out that 0.4 was left over. You do some subtraction, you do some math. And then to figure out your concentration of, this is also equal to N for the nickel. So to figure out your concentration, all we have to do is divide your millimoles by our volume of nickel, which it says there is 25 milliliters. And that's going to equal 0.03664 molar. And there you go. Like I said, this is like, you know, it's like a titration problem, but there's a little bit more thinking, a little bit more working, one or two more numbers. I'm not going to go through practice problems with these other methods, but there are several other ways in which you can utilize a metal ion indicator. Specifically, what I like is that it seems like these metal ion indicators come with their own baggage, like their own things that have to be accounted for. But what's neat is that for each thing that has to be accounted for, there's apparently a solution by enough planning. So for example, if the metal that you're trying to analyze doesn't have an indicator, well, you could do something called displacement titration. So the idea is like for mercury, there is no metal ion indicator. The thing that's missing on that original table, I'm going to go back and confirm that it's missing, and I didn't just, yeah. It doesn't say, but not every indicator binds every metal. So there it's unlike an acid-base indicator. It'd be kind of weird if there was like an indicator that only bound hydroxide and didn't indicate hydrogen. It doesn't work. It doesn't make any sense. So like if you had like mercury, what you could do is you just go and you treat it with excess EDTA, and then you take that sample and then you use some other metal to figure out the amount of excess. This is a little bit like a back titration, except you're not necessarily like, it doesn't quite work the same way because like, so that one does feel like a back titration, but like for example, the silver ion, again, no indicator. What you can do is you could treat it with say a cyanide complex, which silver has a high affinity for cyanide, and it will bump out another metal, and then you can analyze the other metal with EDTA. So like the second example is better, where the idea is you're using EDTA to measure the metal that was bumped out instead of measuring the metal that you actually want to analyze, and that's why they call it displacement. Something else, like an indirect titration. This feels a lot like a gravimetric analysis almost. You can actually use metal ion indicators and EDTA to titrate to figure out anion concentrations. For example, you take a sulfate, you treat it with excess barium, like you guys did in the AP lab. You take a sample of an amount of EDTA and you trap all of the excess barium, back titrate to figure out how much excess EDTA there was, how much barium, sorry, I said too many excesses. The idea is you have like a sulfate sample, you hit it with barium, you have your solid. You take your solid, you hit that with EDTA, it knocks loose all of the barium, and now you have an amount of trapped barium that's equal to your amount of sulfate. By back titration, you can eventually figure out the amount of barium you have, and then therefore the amount of sulfate that was originally present. The final one we're going to talk about is masking, and that's where you have like a mixture of metals and you want to quantify both or quantify one. And the idea is like, so while some of these indicators don't react with certain metals, there are some that react with several metals. And so if you had a mixture of metals, you can't really do anything. Or you know, you have two things that are both pH sensitive. So if you had, like, say, a mixture of aluminum and magnesium, what you do is you add another compound that selectively reacts with one of them, like we did in chapter, I want to say it was chapter 6, that selective precipitation. For example, fluoride will react to make aluminum fluoride solid well before any magnesium fluoride occurs. And then once you've trapped your aluminum fluoride, you can either filter it out and then go do other process with it, or if it's trapped enough and you're not going to see it in your titration, you can titrate the magnesiums that's there. You could then maybe play around with the pH to liberate your aluminum ions again. For example, at low pHs, you'll start making hydrofluoric acid, which would liberate your aluminum, and then you could titrate your aluminum ion with a second sample of EDTA, and then math, headache, headache, answer. A lot of these are all founded in the same MAVA equals MBVB, just with like another tier or two of thought and calculation. I really wish we get a chance to try some of these. Of course, in the third example of masking, if you were creating hydrofluoric acid as a byproduct, I don't think that's going to go very well in a high school lab, but I don't know. Let me sit back and do some planning and see what I can come up with. That said, I hope this illuminates a little bit more how broad the world of titration could be once you stop worrying about acids and bases. Thanks for watching.